Hello friends, today we will discuss about central concepts of automata theory. Before going into deep of automata theory, there are some basic concepts which we must know. The definition of some things which are to be used throughout the class of automata. So it is necessary for all of us to know about these concepts, and these concepts are named as central concepts of automata theory. First, we will discuss about these concepts of automata theory. Before going deep into the concept, first we will know what is automata theory. Why there is a need to study automata theory, and what does actually the automata theory means. The automata theory may be defined itself with the term automata, or we can say the term automata is derived from an English word that is known as automatic. Automatic means, we all know what does automatic means. Automatic means self-working. So automata theory may be defined as the study of abstract computational devices. Abstract devices are means simplified device, or abstract devices means simplified model of real computation. What we require in real computations, that is simplified in terms of abstract device, and the automata theory mean to the study of these abstract devices. Computations are everywhere, whether you are using your laptop, whether you are using your cell phones, or in nature computation works. So it is must for us to study about these computation, how this work, how we can design the device, how we can design the automatic device to solve these computations. Why abstract models are required? Yes, abstract models are required to simplify the things. For example, let's take an example of a simple computer. This is a simple computer. It is having nothing, just it is having a battery, a switch, and a light bulb. So this is a simple computer. The bulbs in our room, in our home, these work. This is a simplified model of a computer. It is having nothing. Input is given through the switch. When we off the switch, the light circuit is disconnected. Light is disconnected, and when we switch on, it means the electricity is passed to the bulb, and we say that bulb is switch on. Otherwise, the electricity is off, we say that bulb is switch off. So this is the simplified model of a computer, or we can say this is the simplified model of an automatic machine. Here are some devices which we will study throughout the course of automata theory. First one is finite automata. Finite automata is a device with a finite amount of memory. It will be having a finite amount of memory, and it is used to model small computers. For small computers, we use the finite automata. Here the small computers, by small computers I mean the small devices. Second one is push down automata. Push down automata are the devices with infinite memory. These devices having infinite amount of memory that can be accessed in a restricted way, but the access of memory is restricted in some manner. These used to model parsers. Next is Turing machines. Turing machines are the devices. They are also having infinite memory, and there is no restriction to access the memory. They used to model any computer. Any type of computer can be modeled with the help of these Turing machine. And the last one is time-bounded Turing machines. Time-bounded Turing machines are also having infinite memory, but their running time is bounded. They used to model any computer program that runs in a reasonable amount of time. If we have these machines works for the program for which the time is a limitation, then we use time bounded Turing machine. These are some basic machines which we will study in the class of automata theory. First one is alphabet. This is the term, this is the basic term which will be used throughout the automata theory, alphabet. So it is necessary to all of us to know what is alphabet. This alphabet is a finite non-empty set. Yeah, this is a set. Obviously, if it is a set, it will be having some elements. Okay, it will be having some element because it is a finite non-empty set of symbols. So here alphabet is represented with the help of symbol summation, or we can say sigma. We represent the alphabet with symbol sigma. For example, the binary alphabet, we all know the binary alphabet means 0 and 1. So this is the here the binary alphabets are represented. Sigma is equals to, it is a set of 0, 1. The set of all lowercase alphabets, is another symbol A to Z, and summation is sigma is equals to A comma B up to Z. The set of all ASCII character is another example of alphabet. So from this discussion we come to know that alphabet is nothing but a set. This is a set of symbols. They may be numeric symbol, they may be alphanumeric symbol, they may be alphabets or some other type of symbols. But this alphabet is a set which is having some elements, and those elements are known as symbols, or these elements are known as alphabets. Alphabet is a finite non-empty set of symbols, and these symbols are known as alphabet. Next is string. Yeah, here comes the string. String, or sometime we also called it word. Either string or word. String is a finite sequence of symbols chosen from some alphabet. From a set of alphabet, if we choose some finite sequence of symbols, then these is known as string or word. For example, 0, 1, 1, 0, 1 and 1, 1, 1 are strings from the binary alphabet, that is 0, 1. If I have a alphabet set, that is 0, if I have an alphabet set that is 0, A, then strings may be 0, A, 0. If I want to write a 5 string, it is A, 0, A. These all are the strings from alphabet 0, A. Okay, empty string. What is empty string? The string with zero occurrence of symbol is known as the empty string. This string is denoted by a letter epsilon and may be chosen from any alphabet whatsoever. Means empty string is the part of any alphabet set because it does not require any symbol. So if I have alphabet set 0, A, then epsilon will be the string of this alphabet set. If I have the alphabet set 0, 1, then epsilon will be the string of this alphabet set also. Length of a string. What is the length of a string? The number of positions for symbol in the string is known as the length of the string. For example, 0, 1, 1, 0, 1 has length 5 because it is having 5 symbols. There are only, no, sorry, it is not having 5 symbols, it is having 2 symbols, but they are written 5 times. Means number of positions for symbol in the string. There are only 2 symbols 0 and 1 in the string 0, 1, 1, 0, 1, but 5 positions for symbols. Notation of length is W. Modulus W, for example, modulus of 0, 1, 1 is equals to 3 and modulus of epsilon is equals to 0. Here if I have the string 1, 1, 1, 0, 1, 0, then the length of this string will be represented as modulus of 1, 1, 1, 0, 1, 0, and it comes out to be 6. Number of positions for the symbol in a string is known as the length of the string. Next is powers of an alphabet. If sigma is an alphabet, we can express the set of all strings of a certain length from that alphabet by using the exponential notation. Means if I use sigma raised to the power k, it means this is the set of all strings of length k, each of whose is in sigma. Means if sigma is having some symbol, for example, let's say sigma is having some symbol 0, 1. Then sigma raised to the power 1 will be set of all strings having length 1. Means again 0, 1. Sigma raised to the power 0 will always be the epsilon regardless of what alphabet set. I have already told you epsilon is the string for every alphabet. That is, epsilon is the only string of length 0. Epsilon is the only string of length 0 because it does not have any symbol. To explain more length about the power, if sigma is equals to 0, 1, then sigma 1 will be the set of all strings having length 1, that is 0, 1. Sigma 2 will be set of all strings having length 2, and set of all strings from the alphabet set 0, 1 having length 2, that is 0, 0, 0, 1, 1, 0, 1, 2. Similarly, sigma raised to the power 3 will be set of all strings having length 3 from alphabet set 0, 1. That will be 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 1 and so on. There is a confusion may lie between this sigma and sigma raised to the power 1. Both are different. Sigma represent the alphabet and sigma raised to the power 1 is the set of strings. Its members are string, and the member of sigma are symbol and the member of sigma raised to the power 1 are string. This is the basic difference between sigma and sigma raised to the power 1. Now, what is clean star? Clean star, we usually use this term many times in finite automata when we define finite automata, when we define regular languages. Clean star is used. What is this clean star? This clean star is represented with summation raised to the power r or sigma raised to the power r. The set of all strings over alphabet sigma means 0, 1 star. This will be the set of all string epsilon, 0, 1, 0, 0 of any length, all strings of any length. Or in other terms, we can represent sigma star as sigma raised to the power 0 union sigma raised to the power 1 union sigma square union sigma cube up to so on. The symbol of sigma star is called clean star and is named after the mathematician and logician Stephen Cole Kleen. Sigma plus is sigma 1 union sigma 2 excluding sigma 0. Sigma plus is excluding sigma 0 means summation star, sigma star or clean star will be equals to summation plus union epsilon. Summation plus does not include the null string. Sigma star includes the null string. Now, how we define the concatenation? Concatenation operation is defined as follows. If A1, A2, A3 up to An and B1, B2, B3 up to Bm are in clean closure, sigma star, then this is concatenation A1, A2, A3 up to An dot B1, B2, B3 up to Bm may be represented as A1, A2, A3, An, B1, B2, B3, Bm. Thus, strings can be concatenated yielding another string. If x and y be strings, then x dot y denotes concatenation of x and y. Means concatenation operation may be represented with this dot. X dot y denotes the concatenation of x and y, that is the string formed by making a copy of x and following it by a copy of y. For example, let's say we have a string x that is equals to 0, 1, 1, 0, 1 and y that is equals to 1, 1, 0. Then xy will be x followed by y and yx will be y followed by x. For example, let's say we have two strings. First one is p equals to a A, B. From alphabet set sigma A comma B, and Q equals to B, B, Q equals to B, B, Q. Then PQ will be equals to, then it will be BBA. Then PQ will be equals to AAB, A, B, and B, B, A. Similarly, QP will be, B, B, A, B. This is how concatenation operation work. For any string W, the equation epsilon omega W equals to W epsilon equals to W holds, because epsilon is about the null string. That is, epsilon is the identity for concatenation. It means epsilon is the identity for concatenation. When concatenated with any string, it yields the other string as a result. The string will be the same because it is having the null string. Next is languages. We always use the term languages when we study automata. What are these languages? If sigma is an alphabet, then L denotes the language, will be the subset of Kleen closure, sigma star, then L is a formal language over sigma. If L is a subset of sigma star, then L will be the formal language. A possibly finite set of strings, all of which are chosen from sigma star. Or in another word, we can say a language over sigma need not include strings with all symbols of sigma. Thus, a language over sigma is also a language over alphabet, that is a superset of sigma. For example, programming language C, legal programs are a subset of the possible strings that can be formed from the alphabet of the language, is subset of ASCII character. Or we can say any language, English or French, these are the languages. Other language example, the language of all string consisted of n number of zeros followed by n number of ones. That is epsilon. Yes, we can include it in any language. 0, 1, n number of zeros followed by n number of ones. Here 3 zeros followed by 3 ones. The set of string of zeros and 1 with an equal number of each. It may be epsilon 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 0, 1. Here the number of 0 and 1 must be equal. Sigma star is the language for any alphabet sigma. Phi, the empty language, is the language over any alphabet because it is the subset of any alphabet set. Epsilon is the language consisting of only the empty string, is also a language over the alphabet. Phi is not equals to epsilon since phi has no string and epsilon has one, that is known as null string. W consists of an equal number of 0 and equal number of 1s. This is another example how we represent the language. Or here the same language is represented as 0 raised to the power n, 1 raised to the power n for all n greater than equals to 1s. Equal number of 0 followed by equal number of 1s. Here any number of zeros followed by any number of 1s. 0 raised to the power I, 1 raised to the power j. Condition is 0 less than I less than j, means number of 0 cannot exceed the number of 1s. These are the languages. Now here are some important operators on languages. First one is union operator. The union of two languages L and M denoted by L union M. The usual notation we use for union is the set of string. This will also be the set of string that are either in L or M or both. For example, let's say L is 001, 10, 111 and M is null string. This is for epsilon, sorry, I write it here. Epsilon comma 001, then L union M will be simple, the union operation is applied. Summation 001 is for both the string 10 and 111. Either it belongs to L or it belongs to M. We simply take the union. Next one is concatenation. The concatenation of languages of L and M is denoted by L.M or just LM is the set of string that can be found by taking any string in L and concatenating it with any string in M. L and M and now 001, because we are concatenating it with, when we concatenate every string of L with epsilon, then it will be the string of L itself. Now we concatenate 001 with 001, we get this one. Now 10 will be concatenate with 001, we'll get this one. Now 111 is concatenate with 001, we will get this one. This is how concatenation of languages takes place. Now important operators of language, another important operator, that is closure. The closure of any language L is denoted by L star. Similarly, the closure of alphabet sigma is denoted by sigma star. Likewise, the closure of any language L is denoted with L star and represent the set of those strings that can be found by taking any number of strings from L. Possibly with repetition, means same string may be selected more than once and concatenating all of them. If L equals to 0, 1 and L is all strings of 0, and 1. If L equals to 0, 1, 1, then L consists of strings of 0 and 1 such that the 1 comes in pairs. For example, 0, 1, 1, 1, 1, 1, 1, 0. 1 always comes into the pair and epsilon, but not, it cannot be, because here this one is violating, because the strings are 0, 1, 1, or it cannot be, it can never be. Thank you very much. These were the some basic concepts about the automata theory. Whenever we go deep into the automata theory or we start studying automata theory, these are the basic concepts which are required to be understood. So in this lecture I tried to explain these basic concepts of automata theory. Thank you.